So today we're starting the recording for Chapter 12. We're going to learn about oxidation and reduction reactions. So we talked a little bit about oxidation and reduction in general chemistry. We also talked about it a little bit in Organic 1. We're going to dig into what actually oxidation and reduction means in organic chemistry. And we're going to talk a little bit about their mechanisms, but the word mechanism we're going to use pretty loosely because we're not sure of all the details. We can provide evidence for some of the intermediates and the products, but we're not positive how it all works. And so I'll show you the mechanisms that are pretty well understood, and the ones that are not, you do not need to panic about knowing. So how do we define oxidation and reduction? It all has to do with the relative number of CH and CZ bonds in a molecule. And remember that Z is just some sort of electronegative atom, something more electronegative than carbon. If you have oxidation, oxidation increases the number of CZ bonds and or decreases the number of CH bonds. So if your CZ bonds go up in a reaction and your CH bonds go down, it's called an oxidation. Reduction is just the opposite. So reduction reactions have an increase in CH bonds and a decrease in CZ bonds. You should be aware that when something is oxidized, something else has to be reduced to make up for it. Sometimes the thing that's oxidized or reduced is just a reagent that you've added to the reaction, but they always occur in tandem together. If you see a symbol like this over the arrow, that means oxidation. A symbol like this with an H in brackets means reduction. So O in brackets just means you have an oxidation reaction happening. H in brackets means you have a reduction happening. And that's describing what's happening to the hydrocarbon. If you have two carbon atoms that are involved, then you need to count the total number of CH and CZ bonds at both atoms to decide whether it's being oxidized or reduced. A little bit about what reducing agents look like. So what are our options for reducing agents? We know that all reducing agents provide the equivalent of 2 hydrogen atoms. So a total somehow of 2 protons and 2 electrons. And there's 3 ways that can happen. The first way, the simplest type, is just if you add H2. If you add H2 with some sort of metal catalyst, so that the reaction has a surface on which it can happen, that's one way you can do a reduction. So H2 can be a reducing agent. The second way you can have a reducing agent is if you have 2 H pluses, which are essentially protons, and 2 electrons. E minus is an electron, right? So the way that works is using something like an alkali metal. So the alkali metals would be like sodium. That's going to be your source of electrons. And then liquid ammonia is going to be your source of protons. So something like NH3 is going to be your source of protons. These are called dissolving metal reductions because you take the actual sodium metal or lithium metal and you dissolve it in liquid ammonia, really cold temperatures. So that's how this type of reduction works. The third reduction is if you have an H minus and an H plus. So this first hydrogen has 1 proton and 2 electrons. The second hydrogen has 1 proton and 0 electrons. So usually your source of H minus, your source of hydride, is an atom bonded to some sort of metal. So something like sodium borohydride or lithium aluminum hydride. Because it's bonded to a metal, the hydrogen has to be more electronegative than the metal, and so it acts like an H minus. They deliver the H minus, and then you get the H plus, so it gets protonated from something like water or an alcohol, where you have an easily obtainable H plus. So the first type of reaction we're going to talk about is the reduction of alkenes. So double bond. Basically, when you do a reduction of alkene, all that happens is you make it into an alkane. So you're going to break the CC pi bond, and you're going to break the HH sigma bond, so this will have H2, and you're going to add two CH sigma bonds. This only works if you have some sort of metal catalyst. Often palladium on carbon is used. So this is called a catalytic hydrogenation. Catalytic hydrogenation. It's always going to be a syn addition, so it's going to add to the same side because of the way the mechanism works. Let me show you a picture. So here's a picture of the mechanism for how H2 adds to an alkene in hydrogenation, this catalytic hydrogenation. So first you need to have your metal catalyst right here, and your metal catalyst can absorb the hydrogen. So the adsorb, which means it sticks to it. So the hydrogen adsorbs to the metal catalyst right here. The pi bond of this alkene then lines up also on the metal catalyst right next to the hydrogen. And in the next step, these two hydrogen atoms are transferred one at a time to the alkene. And the alkene then breaks off of the metal catalyst to be an alkane. You can see that because the hydrogens are lined up right next to each other on the metal catalyst, that they both have to add to the same side of the alkene. So you end up with syn addition. Reaction is exothermic because those product bonds are stronger than the reactant bonds. So we can measure the heat of hydrogenation to determine the stability of our alkene. So for instance, if I have this molecule, trans-2-butene, and I have this molecule, cis-2-butene. If I add hydrogen with a palladium on carbon catalyst, I'm going to get an alkane, butane. The same thing is going to happen here with cis-butene. The same product will be butane. You can rotate it around and it looks like the same product. If we measure the heat of this reaction, so the amount of heat released for the top one, the amount of heat released for the bottom one, we can compare them. We're making the same product with the same reactants. If the heat released for this trans alkene is smaller than the heat released for the cis alkene, you can tell that the trans alkene must have been more stable to start out with. It was lower in energy to start out with, so the difference in energy is smaller than if it was higher in energy to start out with. So the smaller delta H means that your starting material was more stable. Less crowded double bonds tend to react faster, which you can imagine by seeing that mechanism before there. So if they are less crowded, the hydrogens can get in easier. The other thing you can find out from hydrogenation is degrees of unsaturation. Degrees of unsaturation. So if I have a molecule and I know what the formula is, and I know that it is C5H10. We know there's 1 degree of unsaturation because if it was a totally saturated alkane, it would be C5H12. right? CnH2n plus 2. So we know there's 1 degree of unsaturation, but we don't know whether our molecule is cyclopentane, so it has a ring, or whether it has a double bond somewhere. If you add hydrogen and palladium and look at what the products are, this one does not react. So your cyclopentane will not react, but pentene will react to give you pentane. So if the product is different from the starting material, you can tell by how much hydrogen was absorbed, how many double bonds or triple bonds there were, how many pi bonds there were, so how many degrees of unsaturation came from the pi bonds versus how many came from the rings. You can also use hydrogen and palladium on carbon to reduce to primary alcohols or secondary alcohols, depending on what your carbonyl is. So you can reduce it to an alcohol using a metal catalyst and H2. Alkynes can also be reduced in a similar way to alkenes. So to reduce alkynes, you can reduce them 3. So if you have I'm going to change those H's. Okay. So if you have an alkyne, you can either reduce it all the way down to an alkane, and there's no stereochemistry implied here because you have 2 hydrogens on each end. Or you can reduce it to a transalkene. So reduce it part of the way. Or you can reduce it to a cisalkene. And it's all dependent upon which reagents you use. Okay, what did I do? Go back to my screen. Okay, sorry. It all depends on which reagents you use. So if you want to make an alkane, you can do the same way that you did for alkenes. You can use H2 and palladium on carbon. That will reduce your alkyne all the way down to an alkane. If you want the cis alkene, you can use H2 again, but your catalyst is called the Lindlar catalyst. It's basically a dirty version of the palladium on carbon catalyst, and so it doesn't have as many reactive sites, it's not as active, and so you can end up with an alkene instead of an alkane. You'll only go part of the way, but you'll end up with a cis alkene. If you want to reduce to a transalkene, this is where you get to use the sodium in ammonia reaction. And I'm going to draw out the mechanism for you on the next slide so that you can see how it works, because it's really fun how it makes the transalkene. You have your alkyne, and you have sodium in solution. Now we all know that sodium metal is eager to give up an electron, so it's going to form sodium plus and an electron that's hanging out. This electron is going to attack the carbon. Look, fishhook arrow, only one side because it's only one electron. But 2 electrons are going to move over on to the first carbon. Now you have a carbanion on the left, and it's double bonded now to this carbon on the right that has 1 bonus electron. And so it's really crazy looking, right? But this carbanion can pull off a proton from something. So if you have ammonia in solution, looks like that. These 2 electrons can bond to the hydrogen. Those electrons can go back on the NH2. You've now formed This compound here, you have one of your hydrogens added, and you have a radical. So one electron is a radical. Take another sodium, form sodium plus and an electron. This electron is going to go over here, and now, oh, I should have made that fishhook arrow because it's only one electron. Now you're going to have two electrons there, just like we did in the first part. And we know those two electrons can pick up a proton, so they'll pick up another hydrogen from another ammonia molecule. There's your hydrogen, there's your NH2 minus, and your product is a transalkene. There you go. For those of you who like to keep track of your byproducts, there's two sodium ions hanging around and two NH2 minuses hanging around, so you're going to end up with two sodium amides hanging around. So this always gives the trans product, always, always. The end.